Alright, let's start. Most of this topic will be about Joule-Thomson effect and compressor design. So today I'll be focusing on Joule-Thomson effect. In steady flow energy equation, so we'll be talking about steady flow energy equation, kinetic and potential terms. Steady flow energy equation, again, isenthalpic throttling and Joule-Thomson coefficient. Also about temperature inversion, the relation and its relation to Joule-Thomson effect. As well as, again, not today, but we'll talk about multi-stage compression with intercooling equation and advantages of two-stage adiabatic compression with intercooling. So that's the kind of thing that quite often turns up in the exam. So what's isenthalpic expansion? When you put a gas through an orifice and expands, basically the enthalpy remains constant. So that's isenthalpic expansion. Now, that's not really what happens in the real world, but for the sake of this course, that's what we will be looking at. We'll look at real gases as well, but not in too much detail. So this is also the flow through porous plugs, porous media. So if you're a reservoir engineer, the amount of gas going through your rocks, also filtrate in typical chemical engineering processes, filtration, very much affects the oil and gas industry, especially obviously gas processing. So flow going through partially closed valves. In this case, no heat or work exchange with the surrounding systems, and the gas gets throttled, and it's called Joule-Thomson expansion. So you have the gas. Imagine the gas going through this pipe, and then there is a kink in that pipe, so it gets throttled, and then expands again. So if all of you guys try to walk out of that door, and there's a fire alarm, first, you'll run towards it, then you'll slow down, and then you'll speed up again as soon as you come out. Now, there is that speeding up affects the temperature of the gas, of real gases. So the gas must follow a line of constant enthalpy throughout this whole pipe, as long as there's no major changes in the way the pipe is structured, so no elbows, no things like that. And the throttling is almost always isenthalpic in this case. I want to talk about who Joule and Thomson are. So the temperature rises initially. So the gas, now this is the typical Joule-Thomson effect. Now by the end of this lecture, I'll talk about when the temperature rises, when the temperature drops, that kind of thing. But initially the temperature rises, and then the temperature falls. So at lower, the pressure gets lower as it expands, and the temperature drops. And at peak temperature, you can see inversion. Now we'll talk about inversions in a bit. I think it just mentioned. And this expansion effect, the change in temperature, is called Joule-Thomson effect. This is probably one of the most important things you'll study in regards to, if you ever want to go into the oil and gas industry, Joule-Thomson effect is the most important thing you'll study. For example, if you have these major pipelines, you have this valve, and the pressure drops after this valve, so all of a sudden you have cooling in that pipe. What do you think happens? For example, if you have a gas with a bit of water, have you guys ever heard of gas hydrates? Hands up, gas hydrates. Anyone? No. All right. So if you have water, when you process gas, there's water in there, and as the gas flows, as soon when the pressure drops, but also the temperature drops, then these water molecules will form these hydrates, these clathrates, the cages around the water. All of a sudden you get a blockage. Now, as soon as this blockage can build up, and then when you heat it up to remove it, it can shoot through your pipe going 300, 400 kilometers an hour. When it hits an elbow, it's going to be a major explosion. A lot of people will die. So remember Joule-Thomson effects. Affects quite a few other things, but we'll go back to processing, chemical processing in a bit. So it's used in refrigeration quite often as well. Not always, it's not as exciting always. So we talk about multi-stage adiabatic compression. Now these are gases compressed in series, a series of stages. Each stage is a separate compressor, and each compression stage is adiabatic for this course at least. In multi-stage adiabatic compressors, the gas leaves the press compressor. There's usually intercooling in between, so because you're compressing, the gas heats up, so opposite of Joule-Thomson effect. And the gas enters the second compressor at the higher pressure, and basically you have these in series, so higher pressure, even higher pressure, higher pressure. You can have rotodynamic compressors, as you remember. Then these are larger flows and lower pressures, and reciprocating compressors are smaller flows and higher pressures. Remember that for your design. Now back to Joule-Thomson expansion. These are throttled flows, so through a restriction, remember. Through a valve, orifice, porous plug. So imagine you have this valve, you have the boundary around the valve, and the pressure drops across the throttle device. So the second pressure is smaller than the initial pressure. So P2 equals P1 minus the change in pressure. So, and the change in pressure is the pressure drop across this device. This is quite often used for various different calculations, but just remember the principle at the moment at this point, and then third and fourth and fifth year you go through why these are important and how it applies to real gases. Third year especially, thermodynamics. So industrial applications, refrigerators. These can be liquid and gas flow can be controlled using a throttle valve as well. Liquid and gas pressure can also be controlled using a throttle valve, but you need to remember temperature changes. And Linde process is the most commonly used liquefaction process that uses Joule-Thomson effect. Again, you don't need to learn about the Linde process at this point. It comes up in fourth year in energy generation and utilization. I've made all these course materials. So, am I going too fast? All good? Yeah. So, isenthalpic proof. We know that there is one inlet and one outlet. And that should not look like that. So the total energy is the heat input plus the shaft work minus the change in enthalpy, change in potential, and change in kinetic energy. I don't know why that looks like that. So the steady flow, the change in energy is zero. So the energy accumulation is zero in the system. Remember, it's a steady system. So total energy accumulation is zero. Now, with throttling, work is done. I don't know why you have these and signs. They weren't there before. So shaft work is equals zero. So the isenthalpic proof. For the adiabatic process, you know Q equals zero. And for a horizontal pipe, there is no potential energy. It's constant, so it's not falling. And therefore, the change in enthalpy plus the change in kinetic energy equals zero. But the change in kinetic energy is usually considered negligible. Now, we're going to go through the proof why it is negligible and how it is negligible. Second. Hence, the change in enthalpy equals zero, and with throttling is isenthalpic. No change in enthalpy. Yeah. So, from the assumption of ideal gas, the change in kinetic energy equals zero. This is independent from pressure. but that idea is slightly questionable. So we can talk about it being negligible. If we must prove the change in kinetic energy is small enough to be negligible. So an ideal gas isothermal steady state flow is, you can tell, basically the equations are P1 V1 equals P2 V2, and you know P2 equals P1 over V1, and you know how the pressure and volume are related for ideal processes. So if you proceed from there, the drop in pressure due to Joule-Thomson expansion of a device is the change in pressure equals P2 minus P1. You saw that earlier. So sorry. Okay, we're seeing the same thing. So the final pressure is lower than the initial pressure. Substituting that into the previous equation, it gives you the and signs again. The change in pressure equals P1 V1 over V2 minus P2 V2 over P1, right? And hence the change in pressure equals P1 V1 multiplied by 1 over V2 minus P2 V2 over P1 V1 1 over V1. Just substituting. Hence the change in pressure for the system equals P1 V1 multiplied by 1 over V2 minus 1 over V1. Hence, the change in pressure equals negative P1 V2 multiplied by the change in volume from the previous equation, and the change in volume is V2 minus V1. This expression links change in pressure and the change in temperature resulting from the throttling process. And the drop in pressure is directly proportional to the expansion of the gas. So gas expands, pressure drops. Yeah. And the pipe diameter is constant, so the velocity increases with the pressure drop. So as the pressure drops, the more gas it expands, so the velocity of the gas increases. So we can prove that using an example. Is the change in kinetic energy significant? If the change in pressure equals negative P1 over V2 multiplied by the change in volume, we will look at the relationship between the change of pressure and change in energy. So assumption for this is for nitrogen. If the inlet velocity is 10 meters per second, and we know P2 over P1 equals 0.5, so the expansion is multiplied by 2. Calculate the change in enthalpy, change in temperature for nitrogen, and is kinetic energy equals 0? Reasonable. So we know that the molar mass of nitrogen is 28 grams per mole, and the heat capacity of nitrogen is 29 joules per mole per Kelvin. And we know the rate of change for kinetic energy is delta, and the change in kinetic energy equals 1 over 2 m multiplied by velocity the second velocity squared minus the initial velocity squared. And the specific kinetic energy equals the change in kinetic energy equals a half multiplied by second velocity squared minus the initial velocity squared. Hence, if we know the pipe cross-sectional area and we know it's constant, the velocity is equals to this volume over area. So second volume over area, initial volume over area. Substituting the kinetic equation, we have the kinetic equation equals a half multiplied by V2 over A squared minus V1 over A squared, cross-sectional areas. Hence the change in kinetic energy is a half V1 over A squared multiplied by V2 over V1 minus 1. Hence, the change in kinetic energy is a half multiplied velocity, initial velocity squared, P1 over P2 minus squared over minus 1. Now, you've seen this similar equation before, right? So solving for that, you get kinetic energy equals 150 joules per kilogram. And hence 4.2 joules per mole. Minuscule. Going back to throttling, the change in enthalpy plus the change in kinetic energy equals 0, and the molar enthalpy of the fluid is negative 4.2 joules per mole. Hence, assuming ideal gas, enthalpy is a function of temperature and temperature only, and Cp is constant. Remember, for ideality, we assume Cp is constant. So the change in enthalpy equals Cp multiplied by the change in temperature. Hence, the change in temperature is negative 0.14 Kelvin. 0.05% drop in absolute temperature. So change in enthalpy, kinetic energy is negligible. Hence, it's isenthalpic. So there is almost no change in temperature due to the kinetic energy. Now, this changes for real gases quite substantially at higher pressures, but for the sake of this course, negligible, remember. So ideal gas throttling is isothalpic and isothermal, and the change in kinetic energy is directly proportional to initial velocity squared, and the change in temperature is also directly proportional to initial velocity squared. Note, for ideal gases at higher pressure, the temperature changes significantly, and this is more than from kinetic energy alone. This is also observed in Joule-Thomson effect for real gases. I will move on to real gases in a bit. For real gases, the specific energy is a function of temperature and pressure. It's no longer a function of temperature only. So we know the change in enthalpy is equals the change in enthalpy over change in temperature with respect to pressure. All that with respect at constant pressure with respect to temperature, and the change in enthalpy over change in pressure at constant temperature with respect to pressure. Now, for ideal gases, the latter part is 0. There is no pressure. For ideal gases, pressure does not affect the change in enthalpy. We proved that earlier. So if we eliminate the partial derivatives, we can replace these with measurable properties. For example, we know Cp equals the change in enthalpy over the change in temperature at constant pressure. Hence, we can replace that to be the change in enthalpy over change in pressure, constant temperature, which is V minus T multiplied by the change in volume over change in temperature at constant pressure. Now, you don't need to know how to drive that at this point. You'll learn that next year. Fine. If you substitute that, the change in enthalpy equals the change in Cp times the change in temperature plus V minus T multiplied by the change in volume over change in temperature at constant pressure with respect to the change in pressure. Hence, if you take the right-hand side is related to isobaric thermal expansion coefficient alpha. So you can set the right-hand side to alpha. So if alpha is 1 over V multiplied by delta V over delta T with respect at constant pressure, you can simplify that to the change in enthalpy equals Cp dt plus V multiplied by 1 minus T alpha, the change in pressure. Now, that latter, the second part of that equation, the V multiplied by 1 minus T alpha with respect to change in pressure is quite important, and you'll see why. You don't need to fully understand the maths, but you need to remember that. So for an isenthalpic expression, the change in enthalpy is 0, and hence dt equals v over c, negative v over cp multiplied by 1 minus T alpha change in, with respect to change in pressure. So the relationship between temperature and pressure in a line of constant enthalpy, so in your pipe you have a line of constant enthalpy, is the minuscule change in temperature over the minuscule change in pressure with respect to enthalpy, which equals to negative V over Cp multiplied by 1 minus T alpha. You got alpha earlier. Hence, on the left-hand side of your equation, the Joule-Thomson effect coefficient is the minuscule change in temperature, the minuscule change in pressure with respect to enthalpy. And from that, you can calculate, you define the Joule-Thomson coefficient as V over Cp multiplied by T alpha minus 1. Now, remember the T alpha minus 1, and you can define Joule-Thomson effect from that. So, if T alpha minus 1 is larger than 0, your Joule-Thomson coefficient is positive. What does that mean if you have a positive Joule-Thomson effect? What is the most common property of Joule-Thomson effect? So imagine you have a Linde process, or you have a pipeline, and you put a gas, like nitrogen, at 1 atmosphere through it, through an orifice or a valve. What happens on the other side? Yeah. What else happens if Joule-Thomson effect is positive? Linde process, refrigeration. Exactly. So for a positive system, pressure drops, temperature decreases. Positive JT, pressure drop, temperature drop. Be positive. For a negative coefficient, the pressure drops, but the gas temperature rises. Now, this is fairly uncommon because most of the gases which behave like this we don't really use on a daily basis. And I'll mention what gases. And if T alpha minus 1 equals 0, then the Joule-Thomson coefficient is also 0. Now, I'll show you on the graph what that means. But this is the point where the sign changes. So any gas can have a positive and a negative Joule-Thomson effect at a specific pressure and temperature. So for nitrogen, there you go. So for nitrogen, at temperatures over 600, at its supercritical phase. Do you guys know what supercritical means? Hands up if you know what supercritical means. What does it mean? You know it is. Go on. Exactly. So you can't define its property, right? So the pressures or the temperature is so high, you can't define the property. It can be either one. Actually, if you're interested, I do have some videos of my experiments where you go into the supercritical phase. So you have gas, CO2 gas, then you have CO2 liquid, and then all of a sudden you have this thing going. It's this misty thing in your rig where it's actually supercritical because you can't actually define whether it's liquid or gas. It behaves as either one at any one point. So a lot of the times in the oil and gas industry, you'll be working the supercritical phase. Hence, for example, you're sitting there modeling with your Aspen, HYSYS, Pro2, whatever software that you decide to use, and you forget that you're in the supercritical phase. You get the data out, you build your pipeline, and you find out you really screwed up because the density you assume might not be exactly that density. So you might be 20-30% out. You just spend 100,000, 200,000 per compressor, and you have 20 compressors. After getting fired, you're going to jail for a long time. So pay attention to that. Anyway, for nitrogen at 600 degrees Kelvin and pressures above, actually pretty much any pressure, it has a negative Joule-Thomson effect. So it warms up if it goes through constriction. So if you put it through constriction and the pressure drops, all of a sudden it goes way above 600 Kelvin, and you can have some kind of damage to your equipment. But that doesn't happen. What I wanted to show you was where the sign changes. So at any point, at pressures of 50 bar, you have a gas. At 50 bar and 100 degrees Kelvin, you have a liquid. And if you go, as soon as you go over 100 degrees Kelvin, you go into the supercritical region. But within that supercritical region, based on thousands of measurements, you still have a positive Joule-Thomson effect. Now, this applies to most gases, such as natural gas, CO2, but this changes slightly. So remember, this directly applies to your PV diagrams. The units for Joule-Thomson effect are usually Kelvin per Pascal, so the change in temperature in relation to pressure. And these are dependent on the type of gas, the temperature, and the pressure. So for nitrogen at 1 atmosphere, the JT inversion is at 350 degrees, so that inversion at the very top. For oxygen, that's 490 degrees at 1 atmosphere. But for helium, again, one of those uncommon gases, JT inversion is at minus 220 degrees. So at normal temperatures, atmospheric temperatures, the temperature increases when it goes through a constriction. And that applies to hydrogen as well, with an inversion of minus 170 degrees. Joule-Thomson is often used for liquefaction of industrial gases such as O2 and nitrogen. Linde cycle is the most common one, and it uses a series of expansions to bring down the temperature. So it's basically more efficient, and you'll learn, you can calculate why it's more efficient in the future. But these are a series of expansion, and the gas can only be liquefied because it's a positive Joule-Thomson effect. So obviously you'll heat up the gas if it's negative. And you can use for nitrogen and oxygen, you can use the Linde process. Yes, I've watched that advert way too many times. And for helium and hydrogen, it's negative Joule-Thomson effect, so you need to use other cooling requirements. You can also use the Linde process, but you have to modify it significantly, and they do. Thank you, and we can move on to tutorials.